Hi, Dr. Huckabee again. This is a lecture that I gave this is the second half of a lecture that I gave last semester, and it's on Chapter 3. Please pay attention and make sure you get all you can from this lecture. In addition, I'm going to share with you your to-do list. So your to-do list is to do homework 4, which is due on Friday. Work as many Chapter 1 through problems as you can. Hopefully you're able to work all of them with no problems. Work the old exam and practice exam problems, as well as make sure that you know what your learning objectives are from these 3 chapters. Don't forget, we have an exam on September 15th. So good luck, all.
One thing that's much more valuable in organic chemistry is not just comparing pKa's or trying to guess what is the most acidic, but to actually make it mean something for a reaction. And this is something I think that you've seen in your homework for this week, and that is if you have A plus B in equilibrium with C plus D. And you say to yourself, okay, I know one is an acid because it has a lone pair, and I know that one is a base. Wait a minute. Yeah, that's done. Whoopsies. You know that one is an acid because it has a proton, right? Everybody followed that blunder. And one is a base because it has a lone pair. And you also know that the base physically plucks the proton from the acid, and then you have some conjugate base. Again, I did it again. You have some conjugate acid with a plus charge and some conjugate base with now a minus charge because it lost its proton. Okay, so this is clearly a very vague reaction, but hopefully using REO you can see which side of the reactants or which side of the reaction is favored no matter what A, B, C, and D are, because you can use these rules every time. And if it seems like this is all the same stuff and I'm just kind of giving you the same information 5 times, there's a reason to it because of how important it is for the rest of this year of organic chemistry that you've decided to take. Because all of this is what you need to know here on out for the next year. Okay, this is organic chemistry right here. So using REO tells you whether the products are favored or the reactants. Oh, wrong side. There we go. And most practically, you can use it for types of reactions like this, where you have, oh, I want that to be the base. Whew, that's a rough day for drawing. Okay. Yeah, we have an alkoxide plus phenol. And that's in equilibrium with the conjugate base of phenol there, and the conjugate acid of this trifluoroethanol there we go, getting through it. Okay, so a lot of questions about the last homework were, you know, how do you get that series of sentences to work out to which side is favored? Because we say a more stable conjugate base means a more acidic acid, which means something, right? So to get that to actually click, you can use the REO rules to find which side has the more stable conjugate base, and that side should be the one that is favored, right? Okay, good. I'm already seeing some nodding. That's a good sign. Some people have thought about this already. So using this example, all right, using this example, We're going to do this together. We can do this. We got this. We have the power. Let's find the acids first. Or do you want to find the conjugate bases first? Who votes for acids? Hands up high. Yeah. Okay, I'm seeing some acids. Who votes for just using a conjugate base first? Okay, seeing some. The good news is it doesn't actually matter which one you pick, because you find an acid, and then the first step you do once you identify the acid is to make the conjugate base. Okay, so for instance, here we know that the acid is the phenol. The conjugate base of phenol is the phenolate, right? The alkoxide here is the base, and its conjugate acid is this alcohol. So we know that the two acids that we're dealing with are the phenol and the alcohol. But newsflash, you're going to use the conjugate base anyway. Just you could use the bases on each side. So you know the base here and the conjugate base. It's already there. All the information is already there that you need. So let's just go with using the base and the conjugate base. So if we take those two, yeah, this time I got it. Oh no, I can't remember. Are negatives blue or red today? They're blue? Alright, good. Didn't want to forget that. That was super important. Alright, so that's one conjugate base, and the other was the phenol, right? Good, we got a good blue negative charge there. Okay. Now we want to compare the REO, right? So, because if we do REO, we'll know which conjugate base is more stable. So, we'll do A, R, I, O. Great. Atom. Which, is there a difference in atoms? No. Seeing a bunch of head shaking. That's great. You guys are on top of it. No. What about resonance? Any resonance differences? Shaking, nodding. Okay. Very timid nodding. All right. There is, in fact, big resonance difference here because this phenol, those lone pair electrons, can go all around the ring to make many different resonance structures. Here is one. Yeah, seems right. Oh, almost did it. Almost did a bad thing. There we are. Blue negatives. And we could continue doing that all around if we wanted to. Why not? We'll just put the negative on the other side. Yeah, thank you. Sorry about that. Boom, boom. Okay. Hopefully, did anyone not see how I arrived at both resonance structures? Here's a sneaky problem for you. In your mind, right now, can you see the third structure that I didn't write? Really take a second and see if you can visualize the structure that I did not write down, because you need to be able to draw resonance structures. I really should have had the Jeopardy music queued up here, right? All right, I'll give you, so I'll time you 20 seconds. Can you take these 20 seconds and win for yourself some nice brain points? If not, that's fine, because after 20 seconds, you will know the answer. T minus 10. All right. So in case you missed it, what you could have done, I'll just redraw this structure here in the middle. That's what we had, right? What you could have done, move this pair down, move this one onto this carbon. Oop, almost did it again. Bad. There we go. Hopefully everybody saw that. If you didn't, please practice more, because you need to be able to see these resonance structures and see how to just move the electrons around. It's kind of, maybe a kind of helpful pattern would be just to observe that it's kind of an opposite, there's like an opposite relationship between which carbons can have the lone pair on them. Because if you noticed, every time electrons come down, the next lone pair that can exist is 2 carbons away. Right? So let's redraw just this section here. So what I mean is, if you remember the allyl anion, which is one of like the first resonance pattern we saw, every time you move down a lone pair, the third carbon could be the next lone pair. It could have the next lone pair, and that's going to be true for basically any conjugated system. Where were we? All right. So resonance. Yeah. So the phenol has a much larger resonance contribution than does the alcohol. So I'll just write P for phenol. What about induction? Do either of them have a big induction effect? Good. I'm seeing some nodding. Some people are still here with me. You're not all asleep yet. Yes. Which one has it? Is it the alcohol or the phenol? Raise your hands for alcohol. All right. I'm seeing some alcohol. What about phenol? Good. I saw 0 for phenol. Great. You're right. It's the alcohol, and that's because this carbon, the one next to the negative charge, is next to a carbon that has a whole bunch of fluorines on it. So even though that sounds complicated, if you draw the dipole for this carbon, it's going to be hugely in favor of the fluorines, right? That partial positive means that in some way the carbon it's next to is going to try and make up for that, to help his friend out and donate a partial negative charge to him. Because essentially, if you make one charge, just like Newton says, it will have a reaction, and the other side will be to give you a small partial negative charge. So it'll have a partial negative there because there's already a big partial positive on the carbon with 3 fluorines. So because of that partial negative charge helping him out towards that carbon, there's going to be a partial positive charge pointing towards the oxygen that stabilizes that negative charge. And that partial positive will be larger, and so you'll ultimately see a larger dipole going that way. Oh, I did it again. It's not a good day for drawing. I'll just throw all these papers away. So hopefully the induction thing makes a little sense, that the alcohol has the induction advantage. And is there a special orbital that we're worried about? Are they both sp3? Can we put this question out of its misery? Yeah, I think we can. So because R has a higher priority than I, which one is a more stable conjugate base? The second one. That's right, the phenol. Because it's the most stable conjugate base, it is the what? Come on, I'm dying up here. Stronger acid. Good. Great. So that means for our original reaction that we took so long to get to, since the phenol is the strongest acid, we're going to write big arrow towards the products, right? And little arrow towards the reactants. Who sees it? Who's with me? Okay. I'm seeing more hands than not hands, so that's a good sign. I don't know, all that talk about being ill makes me feel weird too, huh? Totally psychological. All right. So now a nice example of REO and how to use it for equilibrium. But luckily for us, that's not all there is to learn about acid bases in this chapter. There's a really fun one, a really fun special case of acid-base magic that's called the leveling effect. It's a vague name that has a very practical meaning. So let's say we take some reaction like water plus dimethylamine. So we'll make it the acid. Or sorry, we'll make it the base. See, there I go again. What is wrong with me today? There we are. All right, so it's in equilibrium with OH minus. Minuses are blue, as we all know. And the now protonated dimethylamide. Okay. This reaction is a good example of the leveling effect, because what this actually means is, let's say you wanted to do an organic chemistry reaction, and what you needed was this deprotonated dimethylamine to do some reaction like, I don't know, deprotonate this hydrogen on acetone. Okay, the pKa of water is around 16, a little less than 16 really, but this pKa is around 23. So which one will be deprotonated first? This is much easier. This is quantitative analysis. You have the numbers. Everybody say it with me. The water is deprotonated, right? You all see that? Because you have a good base. One of the molecules has a lower pKa, so it is the stronger acid. So it will be deprotonated first. So my question to you is, if you wanted to do this reaction, taking this base, dimethylamide, and deprotonating acetone, should you use water as a solvent? Ooh, some people saying no. Do you believe them? They're right. You should not use water as a solvent in this case, because solvents are generally in much larger quantities than the stuff you're trying to do the reactions on. You know, even if you have molar concentrations, like in Gen Chem, you work with like 6 molar acid, right? Do you know what the molarity of water is in water? Water, if you just have like a liter of water, that is actually like 55 moles of water in every liter. So if you calculate the molarity of water in water, which sounds like a totally stupid thing, but you can do it, 55 molar versus, I don't know, any very high concentration is still going to be super high, which means you're still going to have a lot of water molecules for every single reactant you have. Which means that if the base, in this case the amide, has a choice between a water molecule and the thing you actually want to do the reaction, it's probably going to choose the water molecule, just because it will run into that first. And that's the premise of the leveling effect, is that you can only use the strongest acid or base that is allowable by your solvent. In this case, the strongest the strongest acid that's allowable in water is water, right? Any base that's strong enough to deprotonate water will do it. If you use a weaker base, say, I don't know, acetate, with a pKa of, oh, it's not up there anymore. Right, the conjugate base of acetic acid up here, the pKa is lower, so it's not going to deprotonate water. But unfortunately, in this case, it also won't deprotonate your acetone. So, and the leveling effect says you can't go any higher or lower than what's allowed by your solvent. I'm showing a basic reaction here that is hindered by water, but it can also be the same for acidic reactions too. Because if we go back to water again, you are fighting the leveling effect because of water now acting as a base and forming the hydronium ion. Oh no, positives are red. There we are. Okay, great. Yep, wheels are falling off. It's Thursday. It's almost test time. Okay, does that make sense a little bit? It's kind of a weird thing because it's again one of these concepts that we're running into for the first time in organic chemistry, but it is one reason why often you have weird solvents for reactions. And if you wanted to do REO on this top reaction, you certainly could. It's fairly easy. First thing you do is ask yourself, what about atom? Is there a more electronegative atom that we're talking about? The answer is yes, right? You guys see that? Oxygen is more electronegative. It takes a negative charge. It's the more stable conjugate base, so water is the stronger acid. All right, good. Glad you can see that. So for instance, hopefully to try and make this more clear, let's say you still want to do this reaction. You tried it the first time, you realized that you were fighting against the general rules of chemistry, so you decided, okay, we're going to take away water. Now, if you run it in a solvent like 1, 2, 3, 4, 5, 6 hexanes, this proton in hexanes has a really high pKa, right? That proton is like 50. So now, as long as you stay underneath 50, the reaction can take place, because if given the choice between this solvent molecule and acetone, the base will take the proton from acetone way before the base from your solvent. That's the leveling effect. All right, so we've talked a lot about REO, and that is primarily how you gauge conjugate base stability. But that's not all, because it wouldn't be a really fun organic chemistry topic if there wasn't a weird exception to the rule. Right, so what if I drew you this molecule? Ethanoate. And I said we're going to compare it to this molecule, tert-butanol, or tert-butanoate. Which one is the more stable conjugate base there? If we do our REO, atom, they're both oxygen, right? So there's no help there. Do either of them have resonance? No. Right? What about induction? Are there any good dipoles that are going to help us out here? No. What about the orbital? Is there any orbital difference? Oh, come on, lights. We're trying hard enough as it is. All right. There. We won the battle again against the lights. All right. There is no orbital difference, right? They're both sp3 orbitals that we're dealing with. So how can we know what is the more stable conjugate base? And the answer is solvation. The leveling effect was the first time we talked about solvents and how they might have a big impact on organic chemistry. This is the second way that they have an impact. It's not a big impact because this is a pretty special case we're talking about, and it's pretty much the only way that it really has an impact. If you have two chemicals that you can't separate using the REO rules, in general, you can say that there's a difference based on how big the molecule is. Okay? So if you imagine you have C with a couple H's, C, H, H, O, that has some size, right? And the negative charge. But if you have this molecule, you have C, C, H. Oh, that should be an H. We're almost there, guys. And then the negatively charged oxygen. Hopefully, from this very crude drawing, you can see the size difference in those two molecules. And so if you're using a polar solvent like water, water is going to be much happy solvating this negatively charged ion than it will be this one. Why? Because all of these CH bonds and the CC bonds are covalent. And they're not even very covalent. There's not much of a dipole between them, which means that there's not a very strong dipole moment, which means water will not want to hang out with them, because water is superpolar. When water is out and about with its friends, it has two lone pairs here, and we remember from our V-separ rules that it has a very strong dipole going up towards those guys, right? So whenever it meets another molecule, it wants to align its dipole with theirs. But it's a lot harder to do that if one molecule has a much larger nonpolar region than the other. So that's one reason why the butanoate, whatever, the deprotonated terbutanol is less stable than the deprotonated ethanol in this case, because it's bigger and water won't solvate it, or sorry, a polar solvent won't solvate it as well. So just like how dipole moments were kind of an additive thing that made certain molecules have different boiling points than others, the size of the nonpolar regions of molecules can cause them to be less stable than smaller molecules. Hopefully that makes some sense if you put it in the same frame of reference as dipole moments. All right, so the last thing for chapter 3, oh no, not the last thing, I lied, sorry. Second to last thing in chapter 3 is a big pet peeve of mine that you will learn about from here on out, and that's the idea of counterions. Because the same way, if you ever come across salt, it's always NaCl, which means sodium plus Cl minus. Oh no, the plus is not red. There we go. The same way you see this ionic compound as salt, if we ever write something like a deprotonated isopropanol with a negative charge, it will always have some counterion. Whether it's sodium or lithium or potassium, some positively charged thing to offset that negative charge. Because in the real world, you cannot make, not cannot, it is very, very hard to make isolated ions. In fact, if you dissolve something and it's an ion, something in the solvent will make up for that charge, because that's just a super high energy thing to just have in the solvent. So in all reality, you will always have a counterion with your charged species. And what this means for you all is, if you have this molecule and you add water, what you make is isopropanol plus OH minus with the same counterion, because you have a minus charge here on the product side, and there is no such thing as just a bare minus. Like there has to have something to offset the charge. You should put that in your brain right now. If you ever see a minus, it better have the same plus that was on the other side. If you have a set of charges on one side, you better have the same charges on the other side. On the left is overall neutral. Negative plus positive equals neutral. So on the right side, you should have another negative plus positive equals neutral. And if you wanted, just because today we're learning about REO, if we do REO on these, again, no atom difference, no resonance difference. Is there an induction difference? No. What about an orbital difference? No. So my question to you is, why does water have a pKa of 15.7 and isopropanol have a pKa of 16? Maybe it would be easier if I brought the Solvation piece of paper back. Remember that? This is another example of Solvation, because water, obviously smaller than isopropanol. So just because of that, it has a slightly smaller pKa. It's a better acid. All right, now the actual last thing before we do something fun and go home. All right, the last thing is we spent the last 2.5 whatever lectures talking about Bronsted acids, right? Proton donors and proton acceptors. But that's not the only type of acid there is. There's also Lewis acids and Lewis bases. It's not something that you will talk about a lot in this class. However, it's something that you should be aware of. A Lewis base is an electron pair donor or acceptor. So Lewis acid bases. So what this means essentially is, instead of dealing with protons, now you're going to be dealing with other atoms. So let's just draw a very simple reaction. Trimethylamine plus boron trichloride. We can draw all the electrons around it. But the trimethylamine is a Lewis base because it donates electrons to the boron to make this molecule, where now you have a positively charged nitrogen and a negatively charged boron, because the nitrogen donated its electrons to the boron. Those are two full plus and negative charges there. And for now, in this chemistry course, that's all you need to know at this point. We'll go over probably a few other examples of Lewis acidity and basicity a little later. But first, well, not first, but lastly, let's talk about something a little more fun. Organic chemistry can be tasty because you can use bicarbonate to make delicious baked goods. And maybe you've noticed in your home or in your parents' house that there's baking powder and there's baking soda. Both of these, I've tripped over that so many times. What is that? I don't even know. Both of these things are based on bicarbonate, as you see up there. And just like our ocean acidification slide from Tuesday, With acid, bicarbonate goes to CO2. And CO2 makes bubbles and makes nice, light, flaky, pastry things, right? So the difference between baking powder and baking soda is just how fast you make the CO2. With baking soda, it's sodium bicarbonate, and as soon as you mix your dry ingredients with the wet ingredients, you start the acid-base reaction, and it starts to make CO2, which, if you're making something like, cookies or scones, you want that immediately because you essentially mix the stuff together and you put it in the oven, right? There's no rise time. With baking soda, there is what's called two double-acting ingredients. You have baking soda plus tartaric acid, or tartrate. So as soon as you add as soon as you mix the dry and the wet ingredients, you have an initial acid-base reaction, but not all of it. The rest of the CO2 is made whenever you apply heat. And so that's why whenever you're making things like biscuits, or in this case, these bao dumpling things, when you apply heat, they rise a little more than they originally did whenever you just mix the ingredients together. So baking soda gives us delicious cookies and scones. Baking powder gives you like biscuits and a little more dense, bready type things.